speaker of the day is Anthony Beach, no stranger to us here at Blue Marble. Anthony has been a long-time user of our software, and he's going to introduce what would be a fairly typical use case for our software. By way of introduction, Mr. Beach has 30 years experience as a private consultant. He's been an avid user of our software since version 13. I think that goes under the category of antique version at this stage. He has taught college-based civil technology courses based on software such as ArcMap, Autodesk, Civil 3D, and he's also embraced the technology in Blue Marble's Blue Marble software, including Global Mapper. He is a Texas licensed professional engineer, certified floodplain manager, and he's been a partner at the company BSP Engineers for the past 25 years. He's been involved in the design and production of hundreds of civil projects with an increasing focus on the municipal government market. In his presentation, as I said, Mr. Beach is going to introduce a typical workflow that BSP engineers use with Global Mapper. Let me reiterate once again, for those of you who weren't here at the start, you can ask questions. That questions panel on the right side is available to you. We will try to read some of those questions at the end of Mr. Beach's presentation. Please try to keep those questions on topic. I know a lot of you have questions for us in general. You can go to our website and get direct communication options for talking to Blue Marble. Please keep the questions coming in relevant to the topic at hand. So with that, let me introduce Anthony Beach. Are you with us, Anthony?
I'm here, David. Can you hear me okay?
Perfectly, loud and clear. It's over to you.
I guess my screen's coming through now.
Perfect, yes.
Okay, great. Thanks, everybody. Thanks, David. Thanks for the introduction. Our talk today is going to be about modernizing engineering workflows, specifically exploiting the drone technology in combination with Global Mapper and the LiDAR module. So that's basically what, in summary, what we're going to be talking about today. So as David said, my name's Anthony Beach. I also go by Tony. I'm a 30-year professional engineer. I've been a senior partner with BSP for the past 20+ years. I'm also a certified floodplain manager and a consultant for many municipalities in Texas. And in a past life, I was a 7-year college level instructor. So what we want to talk about in this presentation is in modernizing engineering workflows. We adopted drone technology about 3 to 4 years ago in 2015. We originally attempted to construct topography from the photogrammetric point clouds only. This process was adequate, but it contained a few issues. So we began searching for a better methodology for using the photogrammetric LiDAR to develop not only accurate, but also lightweight topography to be imported into our civil engineering software. So that's what I want to go over today, and hopefully we'll be able to all leave here with just a little bit of knowledge in regards to that. We created a little video, not sure how it'll come through on the presentation, but this is a little video we put together to kind of show our commitment to the drone technology. This video we put together specifically for this presentation. Hopefully that came through okay for those of you that are watching online. So moving on, this presentation, we're gonna explore a typical workflow created by BSP to create existing topography for use in our Civil 3D software. As of right now, we have adopted the Autodesk Civil 3D software. So that's what we're ultimately trying to get a surface into Autodesk Civil 3D. So in summary, we're going to begin with the process of collecting some aerial imagery via drones, generating a point cloud, and from the point cloud, we're going to extract feature lines. Some of us call this a break line, and then we will end with a lightweight and accurate topography surface model. So the particular project we're looking at, this is a real world project. So this was a project that we are doing for the state of Texas Department of Transportation, and it's basically US Highway 79. The majority of this project goes through the city of Rockdale, Texas. I'm speaking to you today from Temple, Texas, which is about an hour's north of Austin, Texas. So this project included the reconstruction of about 2 3/4 miles of Highway 79 that traverses through Rockdale, Texas. This right here is just the cover sheet of our overall plan set. This is one of the sheets within the plan set, showing a close-up of the design going through the downtown district. And I'd like to call your attention to the parking, and notice the star in the left intersection. So that is an actual part of the project that's going to be incorporated, but I have a little bit better exhibit that will explain how the star and all these downtown buildings fit together. So this is a 3D model that we developed in SketchUp. Note all the buildings. The buildings were put in from the point cloud information as far as their heights and the configuration of the building. But this is that same intersection that we looked at that has been incorporated into the plans. This is the downtown Rockdale portion, showing the parking, the sidewalks, the ADA ramps, and the overall general design of the project. So today, we're going to go over using this technology with the Global Mapper and the LiDAR module. So the first step is we're going to acquire the drone aerial photos. We'll discuss that briefly. We could discuss acquiring UAV aerial photos for easily over the next hour. There is a lot involved in that, but we're going to have one slide in regards to that and just basically give an overview of what that process is. The next item will take the UAV aerial photos and develop point clouds and orthomosaic imagery. So it will stitch together all of the different photos and create one large orthomosaic imagery that we end up using as a background in our overall design drawings. Then we're going to get in more specific, and we're going to look at using Global Mapper and the Path Profile tool. There's been a lot of improvements to that tool recently, and we'll talk about some of those in our presentation. While we're in the Path Profile tool, we're going to learn or see a few slides on how you actually digitize and extract features from the point cloud data. Then we'll learn how to create a DTM from the point cloud and the extracted feature lines. Again, we'll call those break lines. And then we'll develop a 5-foot point grid from the DTM. An interesting note here, in Global Mapper version 20.1, there is a new LiDAR thinning capability. So we actually used that as an option for also developing this five-foot point grid. And it creates a very accurate but yet a lightweight topography surface. And we'll show the use of that in one of our slides here coming up. And then the last item to this workflow is exporting these new feature lines or break lines, including the points, the 5-foot point grid, and importing them into our civil engineering software. Right now, we have adopted Civil 3D, and that's the Autodesk software that we use for the production of our construction plans. So the step number one is acquire the UAV aerial photos. This is sometimes called photogrammetric LiDAR. So obviously the first thing you need to do to collect aerial photos is you need a commercial drone pilot license. We have that in-house. We are Part 107 drone pilots here at BSP. Obviously, before you get out and fly your project, we need to check our airspace. So in general, there are different classes of airspace. Free airspace up to 400 feet is called G airspace. So most of this particular project, we did have G airspace, so it wasn't a lot of issues with getting our clearance for flying our drone. The next important step would be placing ground control points. As you can see in the photo, the target, the plastic target that you see on the ground, are the typical targets that we use for placing ground control points. So we'll actually, with our GPS technology, we'll acquire an XYZ information on each of these ground control points, or aerial panels we call them, and then that will be used to get a more accurate point cloud. This particular project, as you can see, we used DJI Phantom 4 Pro. We have since used different drones, but this particular project we were using the Phantom 4 Pro. Then you'll need to choose the photo collection app on your iOS or Android device in order to fly the drone and actually collect the photos. And there's several options for that. We'll go over those soon. And then ultimately you need to fly the mission. This was a challenge because we had 2.7 miles of linear highway. So we actually flew this mission in 3 different parts and then stitched the missions together using the Pix4D software. And we'll talk a little bit about that coming up. So after we fly the mission and bring it into the software, as you can see, you can see all the different photos that were taken, their XYZ locations, and a preliminary point cloud. So this is what you end up with when you process your photos to start the surface creation or the topography creation in our workflow. So to develop the point cloud and the orthomosaic imagery, there's several options available. Blue Marble, of course, and they have what they call their pixels to points tools. That particular tool wasn't out at the time that this project was developed. I would like to go back and do an experiment and actually use pixels to points and compare the results to this project. There's Pix4D Mapper. That's it's a desktop or online version for converting your photography or your aerial photos into LiDAR and photomosaic imagery. There is another online methodology that is created by Drone Deploy. And through a little bit of research, we actually found a product called Drone Mapper, which is the rapid version is actually free. It's limited to what you can do, but if you have 50 to 100 photos, that's actually a product you can try out for free. The technology to convert the photos into point clouds is a well-known technology, and there's several different pieces of software that are using that technology to create the point clouds. So this project that we're talking about today, which is the highway reconstruction, was constructed through the use of the Pix4D Mapper. So after we created the point cloud in Pix4D, we imported it into Global Mapper. This is the 3D view within Global Mapper showing our point cloud that we imported from the Pix4D environment. If you'll notice, this is showing the highway, and if you'll look to your upper left, you can the density of our points are to where you can actually make out the aerial panel that was placed on the ground. And the aerial panels are what are allowing us to get the accuracy we need to use for civil design. Without the GCPs, we're not able to do that. And this is a little fly through we did for the downtown Rockdale. So all we're doing is in Global Mapper, we're flying through the point cloud that was developed for the downtown area. And hopefully this will come through to a point that that can be seen over the web through this presentation. So now we're actually on Highway 79, flying through the downtown district. This is just a piece of the point cloud. Remember, we developed this in actually 3 different sections. I'll run this one more time just to get a feel of the overall point cloud and its density and what we ended up with from the photogrammetric processing. Okay, so once we have the point cloud and we've cleaned up the point cloud in Global Mapper, now we'll go in and we'll use the path profile tool. So now we're going to get in kind of the specific steps that we use within Global Mapper itself to create feature lines to pull out the existing curb and gutters and other brake lines within the project. And as you can see, The red circle is representing the tool that we'll be using, which is the path profile tool. Keep in mind, as we're using our way of using this path profile tool is by selecting specific locations. So we do not let the software arbitrarily pick sections. We go and pick the sections at manual locations so that we get brake line data at specific points that work for our design process. What I'd like to draw your attention to is, first we go into the settings button within the path profile line of sight. And I'd like to draw your attention to the upper right area of the path profile settings. And we set the perpendicular path length. We call that our section width. So we set the section width to about 10 feet. And the process we're going to go through here is picking up the existing curb and gutter on the roadway. We like to set our, moving down in that dialog box, we like to set our match elevation scale to distance at a factor of 2. It's just a visual that will help us when we're creating the brake lines. And a very important step here is you must toggle on display LiDAR points along the path. Now, this is where the LiDAR module comes in, and you'll actually need the LiDAR module to have this functionality. And then the last setting I'd like to call your attention to is on the distance from path to show, and it's got the brackets normal. We call that the section depth. So that is how deep within the section do you want to see your LiDAR points. I know it's confusing just looking, trying to describe these, so I'll move on, and hopefully there'll be a better understanding of how this actually works. One other setting I want to call your attention to is the perpendicular sampling. This is the perpendicular perpendicular spacing dialog box. And what's important here, you'll notice we toggle on sample elevations at profile vertices only. If you remember, I stated how we actually determine where the actual profile vertices are when we're creating our brake lines. So this is the setting that you need to make sure is toggled on. Once you get that toggled on, we're ready to start the extraction of lines. And as you can see in the bottom, we're looking at the tool that's required to actually extract the lines from the point cloud. So we're going to select the Add button within the perpendicular profile extraction window, and in the process that we're using, we're using line features in lieu of area features. So for the type, we pick line feature, and then you can set your line color at this point. And we're going to be extracting 3 different feature lines, so we would use 3 different colors. We typically use red, green, and blue. This slide it shows if you look at the bottom of the legend, you'll see we have a 10-foot width of point cloud data. And what creates the density of the point cloud data is the depth that we chose. And we choose approximately 2 to 3 feet, depending on the density of the point cloud, so that you get enough data so that you can see the actual element that you're trying to digitize. So at this point, we would just move through each of the pre-selected locations, and the small red dot you see at the center of the screen, you will actually drag that dot to the desired point of the feature. So in this case, that red dot is reflecting the back of curb. You may or may not be able to see right in the center is a yellow dot. That is where we actually selected on the 2D image where we thought the back of curb was. But at this point, we can refine that location both in X and Y and in Z. So we have just set one vertex for the feature line. And then we advance through this process to create all the different feature lines that represent this curb and gutter. So when you repeat that process, you end up with a set of feature lines that are reflected in this slide. As you can see, we have 3 feature lines that are defining the curb and gutter, both the back of curb, the face of curb, and then the lip of curb. So now that we've got these feature lines extracted, that's a major part of creating the lightweight and accurate topography. The next step, number 5, was to create a DTM from the point cloud and from the feature lines. As you can see in that DTM, notice how the roadway is perfectly smooth, because the roadway we actually developed using feature lines and not the point cloud data. The point cloud data has the irregularity that creates a very bumpy type of a roadway, but as we all know, man-made surfaces are very smooth. So your concrete and your asphalt and your curb and gutter work much better being defined as a break line or feature line in lieu of a point cloud, which is very irregular. And also, you can see as part of this, in the bottom window, we show a profile of the DTM that's reflecting the curb and gutter. The next step is we develop a 5-foot grid of surface points from the DTM that we created in the previous step. Note, there's also an option here where you can do some LiDAR thinning, and I'll show that in the next slide. But I believe that option was just added in the Global Mapper version 20.1. But the red dots you see there are a 5-foot grid of points that we created from the DTM. The whole point of this is to get a more lightweight topography, but yet maintain accuracy. So this is the same area, but in this case, as you see all the dots, those are actually LiDAR points, and we thinned them out to a point that will get the same product as coming up with just a 5-foot grid of points. So this is using the LiDAR thinning that was added in version 20.1.
Machst du nochmal an? Damit ich ein bisschen Hochleistung fahren kann. Nur die erste, nicht die erste Stelle reicht.
So after we get we export the feature lines and the points, we can then bring them into Civil 3D and create a very accurate and lightweight surface within our design software, which ultimately we use to design the overall roadway and create the construction drawings. So as we said, the final result is a lightweight but an accurate existing ground surface that we are now using within Civil 3D. So in summary, we believe that a combination of point cloud data combined with extracted feature data creates an economical solution to providing a lightweight and accurate DTM surface for use in the civil design industry. Notice the word economical. So this is a much quicker way of developing a very labor-intensive process. So what's next on the horizon for BSP? We have now acquired the Phantom 4 RTK, and so what this will do is allow us to do some real-time kinetic drone surveys and actually decrease our processing time when we develop our point clouds from the photogrammetric imagery. Also, we have been investigating the laser bear honeycomb actual LiDAR scanner. So this LiDAR scanner actually is a payload to your drone so that we can, in lieu of getting photogrammetric LiDAR, we would actually be getting conventional LiDAR. Hopefully in a future presentation, we can show the results in Global Mapper, the difference between using the photogrammetric LiDAR creation and the actual conventional LiDAR. So these packages now are getting small enough to actually mount to the drones to actually get your LiDAR information. Thank you. I appreciate it. And at this point, we will attempt to answer any questions or comments that you may have.
Well, thank you very much, Anthony. That was fascinating. It's great to see some of the tools that we use here used in a real situation. There actually were quite a few questions come in, so I'm going to go through some of these. I don't know how many we'll have time for, but we'll go through as many as we can. One question, I think the first question that came in was about your flight planning process. How do you determine the optimal height, or how is that decided?
Sure. The height of your drone will determine your ground sampling distance. So the higher you are, the less ground sampling distance that you have. We typically fly at about 120 feet. We find that to be the best height to get both good ground sampling distance, but yet the data be manageable.
Okay. A couple of questions related to ground control. One specifically about the project you demonstrated, how many ground control points were placed in the downtown corridor featured in the presentation, and a kind of a related question, who decides the number, spacing, and location of the ground control points?
That is a great question, and the way we imagine where our ground control points are, imagine that the project extents is a tabletop. Your ground control points have to be placed as legs to that table, and that table needs to be stable. So if you can imagine, if you have two ground control points in a line, that table will tip over and it will not be stable. So when you're actually placing your ground control points, you have to put them in a spacing or in a grid that would make your tabletop stable. And there is an art to that. This particular project had about 25 control points through the 2.5 miles. The downtown area probably was controlled with 6 to 8 control points.
Okay, great, thank you. More of a layman's question here, but worth asking for folks who are maybe a little bit less familiar with this technology. The question was basically, so the point cloud's created from aerial photos. How does it know elevations was the question. And without going into too much detail of the math behind, maybe you could elaborate a little bit for folks who are not familiar with this technology. How do you know the elevations when you're deriving this from aerial photos?
Yeah, that is actually a function within the software. Just like David said, I don't understand the mathematical equations that are being utilized, but it has to do with the focal points of your camera and the camera knowing its XYZ position. And from that, you can do some math to determine the XYZ of every pixel within the photo.
It is pretty complicated math, and I think we're going to be handing over here in just a few minutes to my colleague Katrina, and she's actually going to be looking at some of the hands-on procedures that will allow you to determine that. So maybe we'll get a little more of a technical explanation by actually looking at the process. We have time for one more question, and this is a very, I guess, opinionated question. I should have prepared you ahead of time, Anthony. Question is, what is Mr. Beach's definition of an accurate DTM? How would you define an accurate DTM?
In this case, the DTM that we end up with is within about 2 centimeters. So that would be in the XY and about 3 centimeters in the Z. So we end up with about 1 inch to 2 inch accurate topography at the end.
Perfect. So once again, thank you very much, Anthony, for your time, and thanks for presenting. It's always, as I said, great to see the tools that we use used in a real-world situation.